Today, I'm going to introduce NQSN Singapore National Quantum Safe Network, a fully interoperable quantum safe network testbed with reference application. So this is a joint effort among different institutes from Security, NUS, Fraunhofer, Singapore, and NTU. This is a joint presentation with my colleague Jing. I will go for the first session, and he will continue for the second section. So here is a recap of the QKD research and industry efforts through the past 2 decades. We can see from the free space to the satellite, and also the recent quantum safe network as a testbed, which is today's talk, as well as the industry quantum safe network. So the mission of our testbed has mainly 4 directions on the pilot infrastructure and the use case. Basically, it's building up the nationwide fiber network with optical ground station that's connected by existing fiber network and with production-grade QKD system. We also have the public and private collaboration on the use case and all the activity with more than 30 government agency and companies. One of the main goals for this testbed is build up a vendor-neutral and multi-protocol testbed to enable different use case and testing scenario for people to try out the quantum safe technology. We also have the hybrid consideration to include both QKD and PQC technology on the testbed. Last, for the infrastructure part, one of the main consideration is on the interoperability. So with the interoperability on the network, we can enable several concepts, including the quantum security, scalability, crypto agility, redundancy, the service, and the support use case, and seamless end-to-end encryption service. Beyond that, we also work on the security evaluation and the function evaluation on the technology, and set up the so-called standard, and the local one and the international one. So here I will give a brief overview on the architecture on our network. Basically, it's aligned with ITU T3800 series, and also the Singapore's local IMDA reference specification. Basically, it has, we consider a 4-layer approach. On the bottom layer, it's a quantum layer, which including the different QKD device connected by the existing fiber infrastructure provided by the NetLink Trust, which is Singapore's fiber network provider. On the upper part, the key established by QKD will submit to the key management layer and the network management layer. This is where the interoperability and the scalability happens for the QKD network. And at the end, the key management layer will finally supply the different symmetry key to the application layer that enable different use case and application scenario. So here, one of the main goals for us is also to demonstrate the full OSI layer integration on the different symmetric encryption technology, from the bottom layer 1 physical to the upper data link, MPS, and layer 3 network, and also the application layer. So I will go through the first 3 layers, the activity on the quantum layer, key management and network management layer, and my colleague will introduce more on the application layer activity. So here is the layout on the basically the fiber infrastructure that connected through the different institutes on the island. So the central node is in security, and to the west, to the NTU and Fraunhofer Singapore, to the east to another university, SUTD, and also several satellite link to the ground station, to some of the startup company and the government agency. So this is basically the layout for the fiber infra. So the summary is that we have included 75 dark fiber. The total length is more than 1,500 kilometer. And the distance range among the link are from 0.5 to 47 kilometer. So let's go to also on the QKD and other layers layouts. This is what looks like for the central node. Correspond to the layer I just mentioned on the 4 layer. We have different production grade QKD system installed, including several company. And we built our own KMS system and network management system. Some of the encryptor are provided by our collaborator, and we also developed some of the in-house application for the purpose to demonstrate and try out all kinds of activity on the QKD network. So I will move on to the first very quickly on the quantum layer activity. So in the quantum layer, we have collected whatever is available on the market on the different protocol, including the BB84, coherent one-way, and CVQKD, and entanglement-based BBM92 QKD. These are the different commercial QKD device that we deployed in the quantum layer. So their performance, we also did some performance tests on the different kind of QKD system. It's quite different, but this is what we have tested, and the results is showing on the right page. We can see based on this kind of performance that will give some challenge on the design of the key management layer to how to have a stable key management supply and to have a stable key supply for the service. Beyond that, we also did further on the more performance and security evaluation on some of the simple tests on the QKD device. Another goal is also to have a long-term performance and stability test over the fiber network to see if it can serve for the real industry usage. So on the right side, the picture is one of the example on the temperature tempering test that we did. So the highlight red zone, it's on the case that we have imposed some of the temperature center change, about around 5 to 8 degrees. But we can see that the interruption could impact on the different parameter, such as count rates, qubit performance, maybe not too much, but the visibility, it's obvious impact, as well as a key rate that every time this temperature change, we can expect some of the change on the system performance. Beyond that, another example we do for the network on the quantum layer part is on the optical switch that we use a fully automated optical switch on the feedback on the several parameter on the reported by the QKD device, that once the quantum channel is degraded, it can automatically switch to the backup fiber link. Beyond that, let's move a bit to the key management layer. This is a fully in-house made up software to support the interoperable operation over the system. And its feature for the multi-input and output key interface with arbitrary topology and the scalability. So there's several functions we realize, including the buffer for the key to be synchronized, and also the key database storage, and also the proactive key relay with a one-time pad and AES to support the key relay among different nodes. We also have the well-known key interface from the ETSI 014 to support the key supply to different kind of application. Beyond that, we also realize a centralized network management system that work with a key management system to realize control and function, management function, including the network control configuration, as well as some of the parameter monitoring. All this activity also has been partially transferred into some of the standardization activity, including the local reference specification on the introduction on what is QKD network and what's the key elements, and also some other international efforts, including the QKD protocol framework standard and the security requirement on the trusted node and the QKD module in ITU and ISO. So far I have been introduced the infrastructure and the standardization activity. So I will pass the floor to my colleague, Dr. Jing, to introduce the use case.
Yeah, thanks, Dr. Hao Qing. So let's move on. So with the infra and also established as well, then now we have the standard to support or as a guideline for our use cases. We proceed to deploy quite a few different activities at different layers as presented just now. For instance, first we using our in-house key management system. We have managed to link up all the different QKD systems together and showcase the interoperability among them. So in particular, over here, what we can see is that all the different tool sites will be able to share the pairwise key among them for different use cases. Another related use case at the bottom is that we use a third-party key management system to establish end-to-end key relay between 5 nodes. So over here, this cover more than 100 kilometers of distance, and we also see that it enables the applications. We also have another cross-border applications that is being enabled by pre-share key, and this also is called distributed symmetric key exchange, and we use it in conjunction with QKD system between Singapore and Canada, Toronto in this case. We have some industry use cases as well. For example, here is a use case for data centers where we showcase that one can actually deploy this kind of QKD system stably in such an environment, and we demonstrated more than 2 gigabit of AES key exchange and also secure file transfer. We have some edge cloud computing applications working together with AWS, and here the result is also featured in their blog as well. Moving on to the OSI layers that we presented just now. So here we have also covering different OSI layers. For instance, at the top left, we have the video, QKD secure video established by MPLS layer 2.5 and layer 3 VPN. On the next application, we also have a 3-node setting where we establish key management system and encryption among them using Singapore local technology. For 5G applications, we have QKD or PQC fallback types of solutions, and we showcase that such an infrastructure can also be secure using quantum safe technology, and we have some streaming and drone applications on top. In progress, we are now also working on optical transport network layer encryption using QKD technology. In terms of hybridization, so we combine the technology of QKD and PQC together. For example, here we have the technology that allows the client to communicate using QKD and PQC encrypted VPN. And we also have some hybridization applications whereby the PQC is being used as a transport of the QKD one-time pad applications. And lastly, we also have defense in-depth applications where we show how QKD enable VPN can also have PQC TLS transport on top of it. Our testbed also support multiple different quantum communications applications. For example, entanglement distribution, single photon source for QKD, and polarization and fiber sensing, and so on. So you can find out more on our website. Our initiative also trigger and initialize another governmental project called NQSN Plus, whereby here there is a platform where they would like to bring this technology to end users and support businesses in Singapore for quantum safe security. And here there are two telcos, Singtel and SPTel, being involved in Singapore, and is also in good alignment with standards and also feature various industry pilots and adoptions. So in a nutshell, we have demonstrated an interoperable testbed, which also support a versatile applications and use cases. And here I would like to acknowledge our funders and also happy to announce that our testbed is now moving on to phase 2 until 2029. And we are also expecting some applications with optical ground station and satellite-based experiments. Thank you.
Thank you. Thank you very much for both speakers. And any question, please?
Thank you for the very interesting talk. Let me ask again the same question as yesterday. Are you interested in a conference key agreement, so multi-user key, or it's not so interesting problem for industry?
Okay, so yeah, actually over there we also say proposals are welcome. So if you have any applications that you can think you can try to utilize the testbed and also our QKD technologies, PQC technology alike, feel free to write to us. We will evaluate and see how we can collaborate together. Yeah.
Okay, thank you.
Yes.
Okay, very last quick question.
Thank you for the nice talk. I have two questions. Firstly, in your slides, so when the temperature change, it will have a larger impact on the circuit rate. So I'm imagining, is there no tolerance on the temperature controlling?
So this is one of the commercial systems we have been used. On this part, it's basically a bit small, but on the temperature change is on the environment change, which is the lowest graph, showing that this from 28 drop from 22. This is due to we open the door, then the temperature drop. But I guess with this range of temperature, the commercial system cannot tolerate that much of change. So the laser and other detector, they got impact. So the system, its direct impact is on the visibility and the detection rate. That will directly result in the reduction in the key rate, even on the interruption on the operation of the QKD. So sometimes it can get restart, so everything will be interrupted.
Oh,
or
okay.
realignment of the things. Yeah.
Okay, thank you. Maybe it will have impact on the time synchronization. Yeah, I just guess. Okay. And my second question is, you mentioned there is a failed try with QKD for the single photon source, and you know there for the quantum dots there will be a cooling system, and it could be very expensive. So what's your opinion in the industry?
Can you repeat the last part of your questions?
I mean, for the QKD with the single photon source,
Yes.
There should be a cooling system. Yes,
okay.
Maybe
Yes.
below about 2 Kelvin degrees. Yes, so this system should be very expensive, and cannot put it in the data center. So what's your opinion? I mean, from the industry's opinion.
Yeah, so I think this one I'll need to bring to our colleagues. So essentially, as you can see over there, the single photon source itself is indeed bulky. So I think they probably will still need some efforts to miniaturize that. There are confocal microscopes and so on to really extract the single photons from quantum dots, for instance. Yes, I think this is likely not rack mountable yet. It's a proof of concept experiment.
Okay.
Yes.
Okay.
But then maybe just one quick point is that over here, we also have silicon chip-based entangled distribution. So whereby there's miniaturization of the systems, let's say for entangled photon source. Yeah.
Okay, it's entanglement source. Okay,
Yes.
okay, thank you.
Okay, so thank you, the speaker, again. And now it's time